2,000 years ago, a Roman soldier could walk from the edge of Scotland to the shores of the Persian Gulf without ever stepping off a paved road. Today, in the countryside outside Rome, you can still drive a car over stones that soldier walked on. Not a reconstruction, not a replica. The original stones laid before Christ was born, still bearing weight, still doing the job they were built for. Meanwhile, a highway repaved last year is already cracking. Potholes bloom every winter like clockwork. Somewhere in your city right now, a road crew is patching a road that was finished less than 5 years ago. The easy answer is that the Romans just built things to last, that they were better craftsmen, more patient, more disciplined than we are. It's a comforting story. It flatters the past and lets the present off the hook. It's also almost entirely wrong. The real answer involves a rock that heals its own wounds, a legal system that made engineers stake their lives on their work, and a design philosophy that modern infrastructure spent 2,000 years quietly abandoning. One that scientists are now racing to relearn, piece by piece, in laboratories in Boston and Rome. By the end of this video, you'll understand why the road under your car is, in a very real sense, built to fail, and why the Romans built theirs not to. Start with the explanation most documentaries stop at. The Romans used massive stone slabs, and that's simply why the roads held up. Picture the Via Appia, its surface made of tightly fitted polygonal blocks of basalt, laid so precisely that you can barely slide a coin between them. It looks indestructible, almost machined. Surely that's the whole secret. Bigger, harder rocks, better fitted. But stone alone doesn't explain 2,000 years of durability. Plenty of stone structures from antiquity have crumbled into rubble, their blocks scattered across hillsides or quarried away entirely. Stone cracks under repeated freeze-thaw cycles, just like anything else does. Water gets into hairline fractures, freezes, expands, and slowly pries the stone apart from the inside. If surface material were the whole story, Roman roads should have shattered centuries ago under exactly the same slow violence that destroys modern pavement. Something else is holding these roads together from underneath, out of sight. The second explanation is manpower. Endless slave and conscript labor, unlimited time, no real budget constraints to speak of. And it's true that some roads took years, even decades, to complete. The Via Appia's original 132-mile stretch was begun in 312 BCE under the censor Appius Claudius Caecus and took well over a decade to finish properly. But raw labor explains how a road gets built. It doesn't explain how a road survives. You can throw 1,000 workers and endless time at a project and still watch it wash out within a decade if the underlying design is flawed. Labor built the road. It did not make the road last. That required something the labor was executing, not something the labor was. The third theory is the one you'll hear most often if you search this topic online. Ancient Roman concrete was just better, somehow. This one is closer to the truth than the first two, but it's usually explained badly, reduced to a single mysterious ingredient, as if Roman engineers stumbled onto magic dust by accident and got lucky. They didn't stumble onto anything. What they built was a layered system, engineered piece by piece, where each layer solved a specific failure mode that modern roads still struggle with today. The stone was never the whole story. The concrete was never the whole story either. It's the combination, and one very specific choice buried inside that combination, that changes everything. So what's actually underneath your feet when you stand on the Via Appia? The first layer of the answer is depth, literal, physical depth, engineered like a foundation rather than a surface. A Roman road wasn't paved. It was excavated. Engineers dug a trench, sometimes 3 feet deep, and built it up in 4 distinct layers. A foundation of large fitted stones called the statumen, then a layer of smaller compacted rubble called the rudus, then a layer of gravel bound with lime mortar called the nucleus, and only at the very top, the fitted paving stones you can actually see and walk on, called the summum dorsum. Think of it less like a road and more like a wall laid on its side, a genuine, load-bearing structure engineered to spread weight downward and outward, so that no single point ever absorbs the full force of a passing cart. A marching legion, or 1,000 freezing winters. Modern roads, by contrast, are frequently built shallow and cheap, a thin layer of asphalt over compacted soil, resurfaced every few years, rather than engineered once, properly, from the ground up. That depth is a large part of why the Roman road survived the earth, shifting and settling beneath it for 2 millennia. But depth alone still doesn't explain why the material itself didn't simply erode away, the way any exposed rock eventually does. That brings us to the second layer, and it's the one modern science only recently began to understand: the concrete itself, and specifically the volcanic ash the Romans mixed into it, called pozzolana, named after the town of Pozzuoli near the Bay of Naples, close to Vesuvius. Roman engineers combined this ash with lime and seawater, and for decades, researchers assumed this simply produced a strong, chemically inert building material, essentially a slightly superior version of modern concrete. Nothing more mysterious than that. Recent analysis, including research published by a team of MIT and Harvard scientists in 2023, found something far stranger sitting inside the material itself. Roman concrete contains small white mineral chunks called lime clasts, and for generations these were dismissed by archaeologists as sloppy manufacturing, as evidence that Roman builders weren't mixing their materials carefully enough. They aren't flaws at all. When water eventually seeps into a crack in the concrete, as water always does over enough time, it reacts chemically with these lime clasts, triggering a reaction that fills the crack with new calcium-rich material, sealing the wound almost as soon as it opens. Modern concrete has no equivalent mechanism. It simply cracks and stays cracked, spreading wider and deeper until a crew eventually tears it out and pours new material on top. The Romans, without any understanding of modern chemistry, without microscopes or lab equipment, accidentally engineered a material with something close to an immune system. But even self-healing concrete needs somewhere for water to go, or it will eventually be overwhelmed by the same freeze-thaw cycles that destroy everything else on Earth's surface. Which brings us to the third layer, and it's the one almost never mentioned in any documentary on this subject: drainage. Roman roads were built with a pronounced camber, a curved cross-section, distinctly higher in the middle than at the edges, engineered so that rainwater sheeted off to either side instead of pooling anywhere on the surface. Alongside many major roads, engineers dug drainage ditches, in some cases lined with fitted stone, specifically to carry that runoff well away from the road's foundation entirely, rather than letting it soak downward into the layers below. Water is, without exaggeration, the single greatest enemy of any road surface ever built. It seeps into microscopic cracks, freezes solid, expands as ice, and tears the surrounding material apart from the inside, invisibly, one freeze cycle at a time. Modern roads fail constantly for exactly this reason: flat surfaces, clogged storm drains, water sitting still and working its slow, invisible war on the pavement from below. The Romans treated water not as an occasional weather problem to manage after the fact, but as the primary structural threat to design against from the very first shovel of dirt. And that leads to the fourth and final layer, the one that's less about physical engineering and more about incentive, because even a brilliant design is only as good as the system that enforces its execution. Roman law, as recorded by the architect and engineer Vitruvius in his treatise on architecture, held builders personally and lastingly accountable for structural failure, not just financially, but sometimes physically. There are accounts, likely part historical record and part cautionary legend, passed down through the profession, describing consequences for bridge or road collapses caused by negligence falling directly and severely on the engineer responsible. Whether every detail in those stories survived intact through 2,000 years of retelling, the underlying incentive structure behind them was very real. There was no simply walking away from bad work and letting someone else deal with the consequences. Compare that directly to a modern contractor who wins a public bid by cutting corners on material thickness, finishes the job on schedule, collects payment, and is long gone before the first pothole appears 3 winters later. The Romans didn't just engineer better roads on paper. They engineered an entire system in which building badly was never a viable long-term strategy for anyone involved. Here's where this stops being ancient trivia and starts becoming a mirror held up to how we build things right now, today, in your own city. Modern infrastructure runs on a fundamentally different incentive structure than Roman infrastructure did. Build it reasonably fast, build it to a minimum acceptable standard, and quietly plan for eventual replacement. Your city's roads aren't failing because humanity has somehow lost the technology to build a road that lasts 50 or 100 years. We could absolutely build that road today. It would simply cost significantly more upfront, and the official approving that year's budget is rarely the same person who has to explain the potholes to angry constituents a decade later. The Roman system aligned the personal incentive of the builder directly with the long-term lifespan of the thing being built. Our modern system frequently does not, and the gap between those two incentive structures is written into the surface of every crumbling road you've ever driven on. This isn't only about asphalt and gravel, either. The same self-healing chemistry discovered hiding inside Roman concrete is now being studied seriously by materials scientists at institutions including MIT as a potential model for an entirely new generation of concrete, for seawalls, for bridge foundations, for coastal infrastructure exposed to constant water damage. If that research scales successfully, it could mean future infrastructure that quietly repairs its own microfractures over time, instead of waiting patiently for a maintenance crew to eventually notice the damage and schedule a patch. A forgotten formula from a Roman engineer's workshop, dismissed for centuries as an accident, might end up embedded in the seawall protecting a coastal city 100 years from now. And there's a quieter implication buried in all of this too. About what? Efficiency actually means when you zoom out far enough. We tend to associate efficiency with speed and low upfront cost, because that's what shows up in this year's budget report. The Romans appear to have understood efficiency very differently. The true cost of a road was never just what it cost to build it, but what it cost across the entire span of time someone might actually need to use it. By that measure, the fastest, cheapest road to build today is very often the most expensive road in existence. It's just that the bill arrives later and gets handed to someone else entirely. Here's the detail that should stay with you long after this video ends. At its peak, the Roman road network spanned over 250,000 miles of construction, enough distance to circle the entire Earth roughly 10 times over. Most of it is gone now, not because the engineering itself failed, but because later generations quarried the stones for other buildings, or simply paved directly over them without any idea of what was sitting underneath. In more than a few towns scattered across modern Europe, the road you'd drive on today is sitting directly on top of a Roman road that is still, quietly, 2,000 years later, doing exactly the job it was engineered to do, holding the ground together underneath a much younger, much weaker road that's already falling apart on top of it. Which raises a stranger question than the one we started with tonight. It isn't only why Roman roads survived this long. It's how much of the ancient world is still down there right now, still functioning, still quietly holding up the world we assume we built entirely ourselves, and how much of it we've simply forgotten to look for. That's the kind of question this channel exists to chase. If you want to keep pulling threads like this one, subscribe to Discovery Loom. We're just getting started on what's buried beneath the things we walk over every single day.